Okay, let's do another example regarding to this conditional probability. I mean, all of you have taken the pattern recognition course. You remember that we had this conditional probability, and we used to call it cross-conditional probability-based classification. So as we can see, the materials that we see in probability, mathematics is always useful in any other field of research. Now, the example is this. We will solve this example in two ways. One of them will be based on what we have discussed in the conditional probability. Another way, we try to philosophically come up with a solution. The question is, a bag contains 10 black and 10 white balls. Draw 3 without replacement what is the probability that all 3 are white? What is the probability that all 3 are white? So, the probability of our event, all 3 are white, is our event. So this probability is actually the multiplication of these probabilities. Probability of first one is white, multiplied by probability of second one is white, given that the first one is also white, multiplied by probability of the third one is a white, given that yes, first and second is white. So we have to multiply these 3 probabilities. Now, first one is white. How many whites do we have? 10. How many balls do we have? 20. Multiply by. Now, probability of the second one is white, given that the first one is white. What does it mean? It means that we have already chosen a ball, and it is white. So, how many white do we have? 9. How many balls do we have? 19. Why? Because it's without replacement. We have taken it out. Multiplied by, what is the third one? How many white balls left? How many balls do we have? 18. So you multiply and you get the result. You multiply and you get the result. Another way of solving this is in this form. Probability of our event is the number of event divided by the number of our sample. Now, what is the number of E? What is the number of E? Number of E means how we can choose 3 white Yes, because we are picking up 3, the combination of the 20 poles when we are picking up 3. So the probability is this. And you will see that these two numbers are the same. You will see that these two numbers are the same. Any question? If you have no question, today we will use the board mainly. Then after that, if you have time, we will go on and review some slides. We will start to talk about marginal probability. What is marginal probability? If now we are seeing a new notation, this means that we have sets A1 till AN, A1 till AN. We show it like this. So it is an equivalent of writing this. If we have A1, A2, AN. So we will use the other notation are mutually exclusive exhaustive and also spanning omega. So we have three terms. We have to describe them before I write down what we want to define about this marginal probability. Mutually exclusive. Okay, page 1. Do you remember what was mutually exclusive? Nastia?
That if one happens better, one doesn't.
No, mutually exclusive. Page 1 means what does it mean?
I think it means that there is no pair of them that could happen at the same time.
Mutually exclusive means that they are disjoint. It means that intersection of any two pairs, if I and J are not equal to each other, is empty. What about exhaustive? If events A, J's are exhaustive, what does it mean? It is a new term.
I think they span all the global sets.
Span is a span. Exhaustive means that at any time, at least one of the events will occur. So it means that we have one of the AJs at any moment. It means we have one of the AJs at any moment. And Morteza, what was the spanning that you were just talking?
All the things, all the samples in the global set are included in at least one of these AJs.
Spanning means that we can divide something in a form that if I add all the division, I will get the whole. It means, Murtaza, that A1 union A2 union AN is equal to omega. In other words, there is not a member in omega which does not belong to any of the AIs. Now, you see, this is long. We are using this notation from now on. We are using this notation from now on. Now, we use another notation. Okay. A's are spanning and they are also mutually exclusive. They are also mutually exclusive. What can we say about the addition? What can we say about, let's say, P of AI union AJ? What is this? They are mutually exclusive. Yes, it's PA I plus PAJ. Now, what if AIs are mutually exclusive, exhaustive, and also spanning? Then we define PBJ. Now, BJ is a set. Is a set which is definitely a subset of omega, right? Look at here. This is my sample space, and this is BJ. Right? Can you tell me that? What is the intersection of any BJ with omega? BJ. So, do we agree that I can write this one as P of BJ intersected by omega? Right? Now, what is omega? What is omega? Yes. It is the union of all the AJs, because AJs are spanning. Right? So I can write it as PBJ is intersection of union now, okay, because we use J here, let me change this one to I, so you understand that they are not necessarily the same things. Now, what I can do, because I know all the AIs are mutually exclusive, I know that they are not intersecting, so I can put this union out. Now, I can put this union out in this form. Something that you have to note. BJ can be a combination of several A's, right? Assume this is A1, A2, A3, and A4. Now, because H1, because all the AIs are mutually exclusive, they are not intersecting with each other, then the intersection of Bj with any of these one will not intersect with each other. In other words, the intersection of Bj and A1 is this part, which does not exist in any other parts. So this means that here all terms are mutually exclusive from each other. Look, AIs are mutually exclusive. When I am intersecting with Bj, I am getting lots of the small parts, but these lots of the small parts are not common. They don't have the common elements because AIs do not have any common elements. Of course, we can have a term like A5 and also A6. Can you tell me what is the intersection of Bj and A5 and A6? Empty, there is no intersection. So those who have intersection, these results of intersection are also mutually exclusive. So if we have mutually exclusive, what is the union? The union is a summation, right? So it means that what I can do, I can write it as, look, I put the union as a summation. And Pbj is known as marginal probability. We will solve examples regarding this one because marginal probability is very useful when we want to talk when we are talking about this joint probability. A proof of these ones, because you will have it with yourself, is not, will not be asked. I don't say that I will not ask proofs, but I don't ask for proofs that I already have done it in class. However, it is useful to know how we are getting this. Because if I only write this one and define it, this is the marginal probability, then your brain can become confused at how we got this one. Now, very important question. Did you understand how we get to this formula, Oscar?
Yes.
Now, let's continue. Okay, keep this one in our hand and let's look at some of the properties of the conditional probability. Because conditional probability is very important. From now on, if I use the mutually exclusive, exhaustive, and spanning, you understand what I mean. Right? Can I erase this part? We need a bigger board. Also, one more notation that I will use. So we agree with that one. Union, we get back into the summation if we have mutually exclusive terms. If we have intersection, we write it as a multiplication. So if I write AI, Bj, it means that there is intersection in between. Now, some useful properties of conditional probabilities. I put some space, so I will write them some definition, some results. Murtaza, if I have AK from 1 to n mutually exclusive, can I say that the union, the probability union of all is 1? No. Mutually exclusive doesn't necessarily mean that we are expanding the space, the sample space. This is something very important. Then now, let's start with the first one. Probability of sample space given B. What is it? We prove it, but let's define it. Let's put it in English. Probability of choosing from the sample space if one of the sample space event has happened. What is it? 1. Because no matter which of the B happens, it's one of the sample space. So it should be 1. But we can prove it by writing that this is the probability of sample space union B intersection B divided by probability of B. Because B is a subset of omega, the intersection is B itself, so it's probability of B over B. And probability of B over probability of B, and it is 1. Now, if A guys are mutually exclusive, then this one can be written as probability of union of I from 1 to n of AI intersected by B divided by probability of B. This is a definition, right? Now, we can write it as probability of union I from 1 till n of AI intersected by B. As I just stated in here, because AIs are mutually exclusive, so the intersection with B will be also mutually exclusive, which means the union can come out and will become a summation. So it will be the summation I from 1 till n of P of AI union B divided by PB. And this is the summation I from 1 till n of PAI union B intersection B divided by PB, which is the final formula, summation I from 1 till n of P of AI given B. So, the probability of the union of AIs given B, look, how we can write this one? We can write it in this form also. P of A1 union A2 union AN given B. So this is this meaning. This is equal to summation of probability of A1 given B plus probability of A2 given B plus probability of AN given B. And we have this condition that AKs are mutually exclusive. Now, the next properties. If AB is empty, then probability of A given B of B given A is again 0. Because it is the probability of intersection of A and B divided by probability of A or B. This is 3. If A is an intersection of B, is a subset of B, then probability of B given A is, then if A is a subset of B, probability of A given B is. If A is a subset of B, what is probability of B given A? This is equal to 1, because this is probability of AB over probability of A, and we know that this means A intersection by B, and because A is a subset of B, the result will be A, so it is probability of A over probability of A, which is 1. What about if A is subset of B, this probability of A given B, what is it? You write in the same way. Here we have probability of A, in the bottom we have probability of B. So it is probability of A given probability of B. Now, by knowing these properties, by knowing the definition of mutually exclusive and exhaustive, we want to define a new theorem, which is called the total probability theorem. Have you heard of this theorem? You don't know.
I have, but I don't know what is it.
I write the theorem, and then I want you to try to think whether you can prove it or not. If B i's, I from 1 till n, are mutually exclusive and exhaustive, then probability of A is the summation of I from 1 to n hint will be start from the right hand side and prove that this will result to PA. And you may need to use the definitions that we have for conditional probability, remembering what is the mutual exclusive and exhaustiveness means. So, from conditional probability, we remember that the probability of A given Bj means probability of A Bj divided by probability of Bj. So, this means that probability of A multiplied by Bj, given Bj multiplied by Bj itself, is probability of A intersected by Bj. Right? So, then the summation of P A given Bj, we are using J here, but we give the index I. So my apologies, so instead of J I'm using I because the index of the summation is I. I from 1 to n multiplied by Bi. This is equal to actually the summation of I from 1 till n of PA intersected by BIs. Now, BIs are mutually exclusive, right? So it means that if I am intersecting A with this BI, the result will be also mutually exclusive, right? So it means the summation of the probability is actually the union of A intersected by BIs. Because A intersected by BIs are mutually exclusive. And this means P A intersected by union of all BIs. This should be exhaustive and spanning omega. Then, okay, what is this? This is omega, sample space. Any subset of omega intersected by omega is itself, right? So, it will be P of, let's write in this form, intersected by omega, which is PA. Now, why we need to know the total probability theorem is because by using this, we can generalize the bias formula, the bias rule that we talked about it on the yesterday class and the slides. Do you remember what was the bias rule? PA intersected by B is PA given B multiplied by PB. Because they are the same, so we said that we can write PA given B is equal to PB given A multiplied by PA divided by PB. Right? This was the first rule. But by knowing the total probability theorem, I will not prove it. If you want, you can prove it at home. The proof is very simple. You just substitute the values. So we can generalize the bias rule by using this total probability theorem and write it in this form. Probability of BI given A is equal to probability of A given BI multiplied by probability of BI. Okay, up to here, we just go right. This should be divided by probability of A, right? But probability of A can be written in this form. So it will be the summation of, let's say, j from 1 till n of probability of A given Bj multiplied by Pbj. Given that the B's are mutually exclusive and exhaustive and spanning also on omega. So this is the general formula for bias rules. A reminder, how we could understand that two events are independent. Two events, yes, AI and BJ are statistically independent if, so if mathematically I want to write it, what do I have to write? Yes, if you want to describe it, we say that the event, the accuracy of one will not affect on the accuracy of the other one. But they are statistically independent if PAI BJ is PAI multiplied by PBJ. What was this? It means the PAI intersected by PBJ. Another form of writing it is PAI given BJ is equal to, if AI and BJ are independent, statistically independent, probability of AI given BJ is PAI. Why? Because accuracy of AI is independent from BJ. We also talked about random variables and cumulative distribution functions. I will do one example. I will write a question and I want you to do it. But before that, do we have any question? I will write the question and I want one of you to come on the board and solve it. Consider the cumulative distribution function of x, where x is a random variable that equals the number on the up base. So I want you to plot the CDF. So what are x? 1 to 6. So do it on your notebooks, and you have a minute or two to do it. So I see while we are reviewing, we are also introducing some new things. Okay, Murtaza. What are the numbers? What is the last one? Just the last one. Okay. There is a slight modification that we need to do. Is this x? The random variable shows the number, right? If x is less than 1. What is the value? 0. But what will happen if x is equal to 1? What is the value? 1 over 6. If x is less than 2, what is the value?
Equal or
Less than 2.
1 over 6?
1 over 6. What about if x is equal to 2? I mean less than equal to 2?
2 over 6.
2 over 6. In other words, we have to draw it in this form. Here it is empty, here it is full. Here it is empty, here it is full. So you have to be careful when you are drawing this one. And as you can see, it starts from minus infinity and it goes to plus infinity. Now, in the slides, you see that the next topic that we want to talk and review is expected value. Then we will talk about correlation and covariance. But before that, we also talk about these joint probabilities. On the next lecture, we want to talk about the CDF of the joint probabilities. Because joint probabilities are very important. We can have two random variables and they are not necessarily independent from each other. So we have to find out how we can calculate and draw the CDF of them. Because CDF has very good application in computer science. For instance, in the image processing, we use the CDF in order to enhance the illumination. Do you have any question? If you have no question, this is the end of the lecture for today. Next week, as I said, we will talk about these joint cumulative distribution functions. We will talk about the expected value, and I also assign you the first set of homework to do. Okay?